There's our lovely, there's our lovely Explore Alliance logo. There's my brother. Hey, welcome everybody to this week's How Do You Know program. I'm Dr. Daniel Barth, and here by the good graces of Explore Alliance. So I want to welcome you. And this week's show is let's just say it's a audience request. And we'll talk more about that as we go. But first, into the science news. And this week, I wanted to take some time and talk about Mars in the news, because there's been some big Mars news coming up. Curiosity rover is now exploring an ancient river delta on Mars. Why is that important? River deltas include silts and clays, which are some of the very best environments for preserving microfossils, regular fossils, organic traces of ancient life. Keep in mind, we know that Mars used to be warm, wet, and habitable, but did it maintain those conditions long enough to develop actual life? And indeed, that's still a question people are struggling with. We've had discussions on How Do You Know before that, so longtime listeners know where I fall on this. I'm very much a fan of the late Dr. Gilbert Levin and his work with the Viking lander on Mars, which was there in 1976. But river deltas are great places to look for signs of ancient life. And Curiosity has been going and drilling cores and they've finally found, excuse me, this last week or so, some of the first cores that they've tagged for the Mars sample return mission, which will come to us sometime in the 2030s, where we're going to be sending a rover to Mars, which will wander around and pick up samples which Curiosity has bagged and tagged in little titanium capsules, and they will be collected in a launch vehicle, blasted off from Mars, and then collected on another ship, orbital transfer, and then it will blast off back to Earth. And after about a 2-year trip back, we'll be able to finally have fresh samples of Mars of our choosing on Earth in full lab facilities that we can look at. Now, we already have samples of Mars on Earth because there have been very large meteor impacts on Mars. Mars has a very thin atmosphere. So blasting things off the planet and out of Martian orbit is easier than it would be for Earth because, 1/3 the gravity and 1% of the atmosphere, things have gotten off the famous Allen Hills meteorite and others. I have a sample of Martian regolith delivered via meteorite in my collection here at the ranch. And these are really exceptional times we live in. We hope governments always promise us this is getting ready for a manned mission to Mars. We'll see. We know how wonderfully governments do with making their promises come true. I frankly think private research firms will make it to Mars before any government does, but we'll see. Time will tell. Another interesting thing on Mars in the last week or so, the Mars InSight lander, which is basically a seismographic station. It's a station that was landed on the Martian soil and drilled into the surface and planted seismic probes, and it's there to watch for Mars quakes. And it's been very successful. It recorded a couple of quakes in excess of 5.0 on the Richter scale recently, which is terrific. Quakes that large send seismic energy echoing and bouncing through the planet and help us to map the interior of Mars, where there are solid, semi-solid, and liquid layers, and explore the interior where we cannot drill. But this week, InSight recorded something really fantastic. They recorded an impact from a meteorite that struck the surface. It created a seismic signature less than 2.0 on the modified Richter scale, which means if you or I were standing there, standing on our feet, we'd be hard pressed to notice. It's very weak, but definitely detectable. And the signature was unique, and we were able to locate where the meteor struck. It's very exciting real time science. And finally, Paul Ingenuity, the little helicopter that could, made its 33rd flight. This little device was expected. They said, "Oh, we want to get like 5 flights out of it, and we're hoping to get 5 minutes of flight time total." And it's now made its 33rd flight. It's covered more than 7 kilometers. That's about 5 miles. So that's quite a feat for a little toy helicopter. And the Ingenuity helicopter, it's never flown more than 12 meters off the ground. And sometimes people say, well, why not? Why doesn't it go higher? First of all, there's no real advantage for it to fly higher. And second, the Martian atmosphere thins out remarkably quickly compared to our terrestrial atmosphere. So flying higher and it gets into thinner air, that's problematic for the little helicopter. And you have to realize we think of air getting thin on terrestrial mountains. People climb up Everest and K2 and places like that, and they take oxygen with them. Well, Mount Olympus actually pokes entirely out of the Martian atmosphere. If you were to walk up the top of Mount Olympus, which wouldn't be particularly challenging in terms of the climb, the slope is never more than about 5 or 6 degrees, but you would be basically hiking across from the edge of Germany to its center, or from the edge of Arizona to its center. And you would be climbing entirely out of the Martian atmosphere. You would be standing in space. So hiking to the top of Mount Olympus, not only would this glorious the crater, the caldera, be visible to you, but if there was a meteor shower, it would be occurring below your feet. You would be looking down at a meteor shower instead of up at one, which is really spectacular. And there we have a little inset video of some of the sample tubes that NASA is talking about there. And finally, Curiosity Rover has sent us back the most breathtaking and detailed panorama that we've ever seen from the Martian surface. I'm a huge fan of these things, and I've been watching these Martian panoramas since the days of Viking in the 1970s. And it's really amazing. You get this camera takes shots, and the camera rotates, and then the images are beamed back to Earth, and computers stitch them together. And over the years, with the various Martian landers from the days of Viking, the first lander on Mars, July 4th, 1976, or July 7th, I think. It was exactly 7 years to the day after we landed on the moon. There's the lovely image. There's the newest panorama. And the glorious thing, we've got links for you in the show notes, folks, where you can link to this. You can download this. And this is a 4K image. This is just outrageous. And you can go ahead and you can zoom in and scan through this thing and move through it. It's just stunning. The next best thing to being there, as the commercials say. So you can search for some of these panoramas. And the nice thing is you can take these and you can photo edit them, and you can take out pieces and make them backgrounds for your computer. And they are quite spectacular for a fan of desert vistas. I enjoy the desert a great deal. I lived in the low desert in California for 30 years, and I hiked in Arizona and California and Joshua Tree and other places, Mojave. And for me, desert panoramas are just the best. And I love looking at these views, to quote Buzz Aldrin, magnificent desolation. But the Martian panoramas are so much more colorful and spectacular than any lunar panorama. Wow. Anyway, so that's the fun from Mars this week. And please download our show notes because we have links there for you about the Curiosity rover exploring the river delta, about the InSight lander detecting Marsquakes, and most recently a meteor impact, the Ingenuity helicopter, which that thing's just great. You know, Paul, I want someday, I want a car the way NASA builds rovers. You know, oh, this is warranted for 90 days, and 10 years later, the darn thing is still running.
I just want a car that doesn't use gas and I don't have to plug it in.
Wow. Okay. Are you hoping for hydrogen? Are you waiting for hydrogen
I
technology?
can do hydrogen. Works for me.
Hydrogen would be fun. It would be especially cool if you hydrolyzed your own homebrew hydrogen, although I'm not sure I would want to brew and store hydrogen in my house.
Yeah, I saw an experiment where a guy took hydrogen and did something, compressed it, and it was like a golf ball amount, and it was boom.
Yeah.
Don't mess with
Yeah.
it.
We did. I did that in my science classes years ago. There wasn't an experiment that used to be common in a chemistry class. Okay.
Yeah.
You would take a paint can, and I'm not going to give all the details because I don't want people to go experimenting at home. But we would put natural gas, methane,
Hmm.
into a 1 gallon, 4 liter steel paint can, and we would light it. We would light a hole, put a hole in the top, and light the gas coming out, and it would burn through. And as it burnt, it basically mixed more oxygen, and finally the flame would go inside, and it would go pop with a nice firecracker type bang, and the paint can lid would fly 6 or 8 feet in the air, and it was surprising and exciting and fun, and lots of principles of chemistry and combustion there. We had at my school, we had a little cylinder of hydrogen, and someone said, "Could we try it with hydrogen?" And I said, "Sure, let's do that."
No.
Um, yeah, the pop was more of a cannon-sized
Yeah.
bang, and it was yeah, the paint can lid went, I don't know, 30, 40 meters into the air.
I mean, it didn't
It was
disintegrate.
No, it did not. The paint can lid is not, it's just a paint can lid. It's
Yeah.
just a press fit. And so it pops off and goes flying off into the wild blue yonder. And we did it out on the football field,
There's
and
so much
bang, pow.
energy in hydrogen. I don't see
Yes.
why we don't use it more often.
It's devilishly tricky to use.
Hmm.
Storing hydrogen, because it is such a tiny, tiny molecule,
Leaks out.
it leaks. The fittings have to be really, really precise. And in an automobile where things are bouncing and bumping around, any leak in the fittings releasing hydrogen, well, you say, oh, hydrogen floats away. But if it leaks into the interior of your automobile, that means you could be generating an explosive atmosphere with, it wouldn't be enough hydrogen to make you pass out, but you
No.
could have an explosive atmosphere with no smell. You wouldn't be able to detect it until you turned on your radio, and then bang. Um, yeah, hydrogen is tricky. The other thing is, if you've got a safe way to store it on board the car, because you don't want to have, say, someone rear ends your car and ruptures the hydrogen tank.
uh,
Bad
that's just
day.
a giant explosion because you've got like
Yeah.
3 gallons in there.
Yeah, exactly. So they talk. There's been metal hydride tanks where the metal hydride holds onto the hydrogen, and you have to heat it up to release it. But it's not straightforward. You've seen like liquefied natural gas for
Yeah.
buses and things like that, and some government vehicles run on liquefied natural gas. That's actually fairly easy to do. Hydrogen takes a lot more engineering.
Hydrogen is
Toyota
such
is
a
big.
renewable energy source,
Yes,
though.
yes. And people have talked about, oh, could I have a hydrogen fuel cell that would generate electricity? But part of the problem is enough amperage in voltage to move a car down the road. We talk about
Uh,
some of these new cars with 800-volt architecture. At one time, automobiles ran on 48 volt because higher voltage transmits with less loss. And it was common to have 48 volts, but people were getting electrocuted working on their own cars, which is why sometime around World War II or just before, or just after, the
12 volt.
automotive industry all switched to 12 volt. And
Yeah,
12 volt became the standard and has been for 80 years.
it hurts
And
a touch, but it doesn't it
it's
doesn't
not going to kill
remove
you.
your hair.
No. Yeah, a 12-volt battery. I suppose you could cause a heart attack if someone was
Yeah.
vulnerable, but it would be an odd circumstance and really unusual to get a lethal zap from a 12-volt system. You'll know
I
you've
still
been bit.
I still say we need to go nuclear, but no one will. That's another topic.
Oh, I think a radioisotope generator. But plutonium's expensive.
You don't need plutonium.
Plutonium's
You
expensive.
need barium, a few other things.
The
We can
problem is
find
getting
something.
enough heat to
Yeah.
generate the electricity you
That's
want.
why they went to uranium and plutonium because it's so radioactive. It just burns.
Yeah, a chunk of plutonium. Ask me how I know sometime. A chunk of plutonium feels as warm as a freshly poured cup of coffee in your hands,
Oh, yeah.
just from its decay. There we go.
You
So
know, what's the byproduct of decayed plutonium? I know you know this.
lead.
Yep, lead.
It's not. It's lead eventually, but
Yeah,
it goes through thorium and
yeah.
oh boy, there's a whole decay sequence.
And it
That's
takes thousands of
long,
years.
long time.
But if you
Takes a
find
very long
lead,
time.
you find lead. Follow that follow that lead stream and you might find plutonium.
Possibly. All right. So let's go to today's topic. 5 times 5 is 20. And why it's true, why it matters. This program came about as a result of a discussion with some of my young teachers. And we were talking about culture in the classroom. Specifically, they've been out observing, they've been seeing sometimes the classroom management is great, other times not so much. And they said, well, Dr. Barth, how do you get out of a situation if you're in one where you have a class that seems to be out of control or a teacher has poor classroom management? What do they do to fix it? And we started talking about culture in the classroom. You have to have a culture of self-discipline, and something I had a sign in my classroom for years that said self-control is always better than imposed control. And I would remind my students of this all the time. And I would remind my students sometimes the whole class would lose a reward if there was poor behavior. Somebody would inevitably, some child would say, oh, but why are we all being punished? Because some of us didn't do anything wrong. I didn't do anything wrong. And I was quick to remind them, you're not being punished, you're just losing a reward. Fine distinctions in behavior there. But I said, the other thing is, you did do something wrong because you failed to stand up for the right thing. You didn't say, be quiet, stop doing that. The teacher will be upset. We'll all lose a reward. When you laugh at the class clown, you encourage that behavior, you reward that behavior, and you're not standing up for the right. And all that's necessary for evil to succeed is that good men do nothing. And a quote there, Google it up, you can track it down. And basically, I would tell the students you need to have a culture where you all correct each other's behavior so I don't have to. And then you're rewarded for doing this. And my students said, well, give us an example. And I said, okay, 5 times 5 is 20. You all know this, right? And at this point, they said, what? Wait, no. 5 times 4 is 20. I said, yes, that's true. But 5 times 5 is also 20. And they said, no, that's not right. I said, oh, you've been lied to? Where did you go to school? Who was your math teacher? Oh my gosh, you didn't learn 5 times 5 is 20. And at this point, they started arguing with me. And I said, okay, well, you'll just have to take my word for it. 5 times 5 is 20. Deliberate ploy on my part. And I went back to talking about culture in the classroom. And a few minutes later, a couple of students raised their hand. I said, yes. And they said, you said you could show us 5 times 5 is 20. I said, yes, of course I can. It just takes a few minutes. And they said, no, it's not. We don't believe it. Prove it. And so I said, okay, which is exactly the result I wanted. I wanted them because now they're engaged. They're asking me, show us, teach us, and they have this moment now where they're engaged. And I said, okay. I pointed this out to them. I said, now you're engaged, so let's talk about this. And I said, first of all, math is problematic because math teaches us things which are philosophically true, but not practically demonstratably true in the real world. And they said, like, and I said, oh, did you ever hear a point has no dimensions? Or there's a perfect circle with an exact radius all the way around? A line is one dimensional and infinitely long? Repeating decimals like 0.3333 go on forever? And the whole idea that a problem can be solved to any level of precision you want. You just have to keep on dividing and carrying the mathematical process, and you can get as many digits of precision as you like. And they said, well, of course we were taught these things. And I said, yeah, except they don't exist in the real world. Because there's something fundamental. Number and measurement are different. They are fundamentally different, and they are so different that they must be treated differently. And we're not taught this in math class. We're not taught about measurement. We're taught about number, which is a philosophically interesting exercise, but there's this big disconnect when we start to take our mathematical methods and then apply them in the real world to measurements where we build things, measure things, analyze things. So in disciplines such as chemistry, physics, astronomy, engineering, all these disciplines where we deal with measurements, we can't treat our measurements the way we treat our numbers. We also have things in math where we say stuff like, you collect baseball cards. John takes half of one less than the number of baseball cards you have. Since you're nice, you give Peter one baseball card. Since her father makes baseball cards, Mary decides to quadruple your baseball cards. And at the end, you have 28. And who the hell talks like that? I remember my son came home with a problem. You have 3 T apples. Sally wants to have 4 X apples, and you decide to divide them up into Z friends. And so, what fraction of an apple does each friend get? And you're like, oh, hell no. Nobody talks like this. This doesn't resemble. Do you remember, Paul, encountering word problems and going, this is such an unrealistic situation. This isn't even the physics problem where we say we drop a rock off of a 25-meter tall building and how fast is it moving when it hits the ground.
I have problems with a lot of the way the test questions and whatnot are formatted. It's like I'm the way I think is so different than other folks. And I'm basically a one-off. And when they ask me this means this, that means this, and this must equal what? And I'm like, lines on a paper. I'm completely, my way I function is completely and so far out of that realm. I can't do those problems because they make absolutely no sense to me.
Yeah, we lose a lot of people with the goofy word problems. But the other issue that I found out teaching physics, chemistry, astronomy, physics class, basic kinematics of objects in motion, speed, time, velocity, velocity, time, acceleration, distance. And there are basic standard formulas. How far does something go when it's accelerating this fast, and all sorts of things. And I would say to a student, okay, here's an equation. Can it's let's say it's v original squared minus v final squared equals 2 times the acceleration times the distance. Can you solve for acceleration? And these were students who were getting B's and A's in calculus, which is an AP level course, and they couldn't rearrange this basic algebraic equation to solve for a particular variable. I would say, well, wait a minute. You're in this pre-calculus, what we would call trig, you and I, Paul. You're in trig class. You're in calculus class. How can you not do this functional algebra? And they would say, but we've never been taught to do anything like this. And the number of students who would just come to a crashing halt because it wasn't a problem with X, Y, and Z was astonished me. And then the other thing is they would say, oh, well, here's my calculator and here's the answer. And the classic one, you drop a rock and it falls 5 meters before striking the ground. How fast is it moving? And the child would ping, 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 ping on their calculator. The rock is moving 1,856.93712 meters per second. And I would stop and say, okay, 1,800 meters per second. Everybody look up the speed of sound. Oh, that's about 700 some meters per 750 meters per second. I said, okay, so let's see. Your rock, after falling 5 meters, is now moving Mach 2.5, something like that.
As it penetrates the Earth's crust and
that's right.
moves into the core.
Yeah, I said, so wow. And I would challenge them like this. And instead of saying, oh, well, I must have done something wrong, they would hold up the calculator and say, no. See, that's the answer. And so 2 problems here. One, we had this fundamental disconnect. So I made this rule that you had to, with your calculator face down on your table, you had to go ahead and make an estimate and write it down. And then afterwards, you had to get your answer and you had to give a match number from 1 to 10, 1 being this answer and my estimate are way the heck off, and 10 being, wow, this was really close. I said, give me an accuracy number from 1 to 10. And we would start talking about building thinking in before calculating. But the issue here, it would fundamentally come down to, and I would tell the students this on the first day, and I would say, well, here's the thing. Chemistry is not a math course. Physics is not a math course. Astronomy is not a math course. And in physics in particular, I would get students who would contradict me and say, well, yes, it is. I was told by my trigonometry teacher or my calculus teacher that when I get into physics, that my skill in trigonometry and calculus will make me a master of physics because it's really just a math course with word problems. And I would like, wow, the big lie. I said, no, it's not. It's not true. And I would start out and tell them measurement is different from number. And when you tell people measurement is different from number, you can tell them all day long until you're blue in the face, measurement is different from number, but students don't get this idea because they have been immersed by the time they hit my physics course, usually in 11th grade, okay? They've been in school for 10 or 11 years. They've been studying math for at least 9 of those, and they have always been immersed in the culture of numbers. And even when there were practical things like here's a ruler, measure something, or here's some coins, count something, or a word problem that says, the train leaves Albuquerque heading due west at 42 kilometers per hour at 9 a.m. One of those classic problems. Even when there's problems like this, every math course treats everything as a number, never as a measurement. And students would say, well, what's the difference? And I used to try to explain this philosophically, intellectually, to tell the kids the difference between measurement and number. But the problem was they were so steeped, literally deeply dyed in the culture of numbers, that they couldn't stop thinking that way. They continued to treat everything as if it were a number. And so fundamentally, you come up with this idea. In order to develop a new way of thinking, you must stop people from thinking the old way. And the same thing with culture in the classroom. This is what I told my students the other afternoon. In order to change the culture in the classroom, you first have to stop and break down the old culture before you can institute a new one. And so I eventually stopped trying to explain this to students. And so on the very first day, I would give them a quiz. And I'm going to go ahead and share a screen here. And I didn't want to do that. I wanted to toggle the screen sharing. There we are, screen 2. I'm going to share. And there it is. And we're going to take a quiz. Now, in American classrooms, and I don't know if this is common in around the world, no idea, but there's been American jurisprudence basically says that if you're in a public school, the government provides everything: paper, pencils, breakfast. And when we were in science classes, we would get rulers. Once upon a time, we used to get little wooden rulers, which I'm sure everyone's familiar with, inches on one side, centimeters on the other. But I would tell the students, okay, we have a ruler, and I would hand out printed rulers that I'd printed out and done myself. And I have one here in my hand. I don't know if you can see this in the inset or not, but nope. Okay, I'll show it. I will show it to you in a bit, but basically it's a ruler which is numbered. It has marks 1 through 10, but only whole numbers. Okay. We think of a typical metric ruler. It's marked in centimeters, but it's also marked in millimeters, so we can accurately measure 3.2 or 4.7 centimeters. But this is marked only in whole numbers. And I tell the students, okay, we've measured some things with our really cheap, lousy ruler, which only measures in whole units, and we're going to multiply these values and get some areas. So, Paul, we're going to go ahead and make you the quiz victim here. So 1 times 5, give me an answer, please.
1 times 5 should be 5.
Correct. Very good. Okay, so that's your answer. 2 times 5, please.
Should be 10.
Good. Okay. And we're just going to go along here. 3 times 5?
15.
Yeah, it's not a trick, really. It's not. 4 times 5?
20.
Good. And 5 times 5, I'm going to, how much?
Just fill it in. I mean, just add 5 to each one. We're good.
Add 5 to each one, says Paul. And most people would start to think this way. And even if it was other numbers than by 5s, which are easy, they would go, oh, well, this is not a problem. 8 times 5, 40. 9 times 5, 45. And so I'd say, okay, now let's go ahead and correct your paper. So 1 times 5 is 5. First answer correct. 2 times 5 is indeed 10. 3 times 5 is, of course, 10. 4 times 5 is, of course, 20. And 5 times 5 is 20. So sorry, you got that one wrong.
I
And
also got the 3x5 wrong.
yes, oh, you did, yes. And 6 times 5 is 30. 7 times 5 is 40. And 8 times 5 is 40. And 9 times 5 is also 40.
Okay.
And so by this time, friends, I had a revolt on my hands.
Yeah.
Students would be saying, no, that's wrong, that's wrong. Let's see, how did we do this last time? Toggle screen sharing? There we are. So by this time, people would be shouting and saying, no, you're wrong. 5 times 5 is not 20, and 3 times 5 is not 10. And what are you thinking? That's just not right. And the thing I would tell them, here's my cheesy government issued paper ruler. And that's not a joke. We were given paper rulers that were on perforated paper to punch out and hand out to students. And here's the problem, Paul. Mathematics, when we're dealing with measurement is different than number, cannot ignore the quality of the tools used to get the measurements. And I would put it to students this way. Let's say you're making a cake that requires 3 eggs, and you've got the flour and you've got the milk, and now you're ready to add the eggs, and you crack the first one, you crack the second one and add it. Then you crack the third one and it smells terrible, but you're 2/3 of the way through making the cake anyway, so you just go ahead and mix it in. I'm just going to make it anyhow. And I ask my students, will the cake be good? Will it be tasty? And they're all like, no, you used a rotten egg. And I said, oh, so the quality of your product is only as good as the ingredients you put into it. And the students would say, of course it is. That's obvious. And I said, well, guess what? When you're calculating with measurements, the quality of your answer cannot be more precise than the level of precision of your tools. And so if your tools are only good to 1 digit of accuracy, guess what? Your answers are only good to 1 digit of accuracy. And so when we look at this and we say, gee, let's take a look at another example here. And I'm going to get rid of this and come on, go away. There we are. Now we can see our printed cruddy government issue ruler marked 1 through 9. And we've got a rectangle here.
I had to buy my own ruler.
Oh,
They
that's
didn't give me
often said in class. That objection, thank you. That objection comes off oftentimes. However, I point out that no matter where you get your ruler, whether it's made from laser precision of the finest quality, there's still a limitation to the accuracy. Can you measure a whole centimeter, 1/10 of a centimeter, 100th of a centimeter? Can you find a ruler that measures 1,000th of a centimeter? Yes, that's called a micrometer. And yes, you can do that, digital calipers, if you will. But at some point, the accuracy of the tool runs out and you're not able to get anything more. When we take a look at this, if we use the ruler we have, and we realize that, whether you're talking about a common wooden ruler marked off in centimeters or the James Webb telescope, the finest infrared precision optical instrument ever made, it has a limit to its accuracy. It has a limit to its accuracy. So let's go on with our example. If we calculate, if we measure and we say, oh, this rectangle here is 1 centimeter wide and 7 centimeters long, and can we find the ratio of width divided by length? And if you go ahead and you take your calculator, and let's turn it on here, And let's go ahead. Can we see the screen? We can. And we do 1 divided by 7 equals, and we get this lovely number here that's many digits long. I have a calculator, a high precision calculator that will display 15 digits of accuracy. And so you say, okay, this answer comes out to be 0.1428571428. And in fact, yes, if you spotted that, it's a repeating decimal. So this calculation gives an irrational answer. It never ends. Or, excuse me, an endlessly repeating. It's not irrational because it does repeat. But we take a look at this, and we take a look at this in terms of decimal places. The first place is indeed 1/10 of a centimeter. Remember, we're multiplying centimeters by centimeters. We're getting an answer in centimeters squared. So the first digit is to 1/10 of a centimeter squared. The third digit over is 1,000th of a centimeter squared. And then we go 3 more digits. We're in the millionth. And then we go 3 more. And we're now in the billionth of a centimeter. My calculator claims my ruler, which is accurate to only 1 centimeter, can give me a mathematical result of measurements that's accurate to a 10 billionth of a centimeter squared. We're talking something, a 10 billionth of a centimeter is 1/100th. It's 1% the size of a helium nucleus. And this is obviously a lie. I cannot measure nuclei with this ruler, nor can any calculation made with measurements gotten from this ruler be accurate down to the size of an atomic nucleus. It's just silly. Of course it can't. No answer can be more accurate than the least accurate factor used in the equation. This is the idea behind something we call significant figures. And this is taught in some science classes, not all of them, and virtually no mathematical classes, no mathematics class I've ever seen has actually taught about significant figures. And when we talk about significant figures, and we look at this answer, and here's how we get back to 5 times 5 is 20. How do we get the answer for 1 divided by 7? The answer is 0.1 square centimeter. Why? Because the two answers have only one significant figure. And when we look at this 5 times 5, each digit has one significant figure. Scroll back a little bit, I think. Scroll back a little bit on your screen there, Paul. There we are. So we see each 5 has just one significant figure. So the only accurate digit in our answer, when we do 5 times 5 on our calculator, we do indeed get 25. But in fact, if we're dealing with measurements, our answer has, with this particular ruler, only one digit of accuracy. So the 2 in the tens place is true. The 5 is not. And we go ahead and we use rules of rounding and we say, oh, 25 rounds down to 20. I'm not going to go deeply into rules of rounding here. That's a whole nother show. But we get this and we say, oh, well, the 0 is just a placeholder. It used to be we did calculations in school with slide rules. And I have several in my collection. I worked with slide rules in physics classes, in chemistry classes, up through college. And then the transition came in the 70s to electronic calculators. And all the slide rules got tossed aside. But a slide rule, a standard slide rule, wasn't good to more than 3 digits of accuracy, no matter what you did. And 3 digits of accuracy was unusual. Usually it was 2 digits of accuracy. But we look at this and we say, oh, our answer is only good to 1 digit here. Well, if we scroll down and we say, how do we know how many significant figures a number has? And this becomes something that's part of the culture of your classroom. That's the culture of scientists, engineers, physicists, chemists, astronomers. The people who build rovers know this stuff intimately. And there are just 3 rules. If it's not a 0, it's significant. If it's a trailing 0 to the right of the decimal point, it's significant. And if there's any zeros in between, they too are significant. And so we take a look and we say, oh, so 5.0 times 5.0 is indeed 25, because 5.0 has 2 significant figures. The second number in the measurement in the calculation, 5.0, has 2 significant figures. And so the answer can have 2. 25 is the correct answer. It would be equally incorrect to say 5.0 times 5.0 is 25.000000. Even if we have a ruler that can measure to 1/10 of a centimeter, we still can't arbitrarily add all those zeros. And when we look at the problem that's on the screen now, we see 1.000 divided by 7.000, and we go, oh, well, in that case, the calculator still gives us the same answer, this unending string of digits, but we realize that, oh, one number has 4 significant figures, one has 3. The least of these is 3. That's the least accurate. And so we have to stop after 0.142. But do we round up or down? We look at the next digit, which we consider to be an estimate. We call it the significator. And we go ahead and we use the significator and we say, oh, the final answer, 0.143. The significator represents an estimate, which we can make. If we look at this ruler and we can say, okay, I can measure something. I'm going to measure the length of this flash drive. And I say, oh, this is about 2.8 centimeters on my low quality ruler. I can estimate the 0.8, but I can't really measure it. I can estimate it. I can use my estimate to decide that, oh, I'm going to round up and say, by this ruler, I'm going to say, gee, this flash drive is 3 centimeters long. I'm using that estimated 0.8 to round up. I'm not going to claim it as a measurement because it's an estimate. Calculators do this all the time. They just continue the calculation out as if everything was perfectly exactly precise. A number rather than a measurement. But when we're dealing with a measurement, we have to go ahead and realize that our answers from our calculating machines are only as good as the data which we put into them. And when we lose sight of the fact that measurement and models are different, then we can run into trouble. Josh says, a measurement tool that measures with a visual reading, assuming a good qualities. My professor said you can use half measures. Again, that's an estimate. And with this, Josh, where you get an estimated value of 2.8, I was told in my quantitative chemistry that I should be able to accurately estimate to the nearest 10th, smaller than the markings. And it depends. But the point is, this is not a measurement, it's a skill. You're depending, Josh, on your skill as an estimator. And if we handed the same tool to Paul here, who doesn't do these sorts of things with measuring tools like this as part of his daily work, he's not going to be as good an estimator as you are. And again,
but I can get close.
Yes. Why is it 5 times 5, 30? 5 times 5 is not 30 because of the rules of rounding. There's rules called statistical rounding and something called the rule of 5. When we're going to use a significator to round up or down, you realize there are only 9 digits that matter. 1 through 9. if your significator is a 0, nothing changes. And sometimes people say, oh, if it's 5 or greater, round up, or if it's 5 or less, round down. But the fact is, if you use that kind of sloppy rounding, you end up rounding up or down more often. And if you're chaining calculations, and yes, we're getting measure at the bottom of the meniscus, which is good chemistry protocol. I don't have a test tube here today or graduated cylinders, so we'll skip that. But again, when we're talking about these sorts of things, if we round up more often than down, we're gradually going to skew our answers higher, especially when we're using a chain of calculations where we take this answer and use it to get the next one. And so we use statistical rounding. 5 is the odd man out because 1 through 4 round down, 6 through 9 round up. 5 makes odd numbers round up, even numbers stay the same. Hence, 5 times 5, the unrounded answer is 25. The 2 is an even digit, it stays the same. Whereas 7 times 5 is 35. The significator again is 5, but the 3 is odd, so we round it up to 40. And in using this rule of 5 or statistical rounding, we don't round up or down more often one than the other. And so over an entire chain of calculations, our answers will tend to be more accurate rather than drifting away from true. These sorts of subtleties of measurement and rounding are important in the culture of science. When we're talking about science, which uses a lot of equations, where we deal with things which are measured, astronomy, physics, chemistry, biochemistry, organic chem, engineering, astrophysics, relativity theory, all these sorts of things where we're dealing with complex answers, particularly when we are dealing with remote sensing, so that they pass the second test or miss 5 times 7 until the next lesson. Josh, this whole teaching about significant figures and correct statistical rounding for 10th and 11th graders takes about a week of practice. We spend the first day breaking down the culture of numbers and showing them where the cracks in the edifice are, how it crumbles and fails when we use the culture of numbers to deal with measurement. And then we take a number of days to practice and show them how the culture of measurement and doing calculations with measurement works. And we continue to re-emphasize this lesson through the entire school year. And students can learn the fundamentals, but to practice until the culture of calculating with measurements is natural takes about a school year. And we continue to re-emphasize it. Every problem set, every week, every laboratory exercise, every day, because they've had 10 years of this culture of philosophical numbers. Numbers are perfect. Numbers are exact. Decimals go on forever. They've had this culture pounded into them for a decade, basically from the time they were first literate. They've had this pounded into them. And in fact, it breaks down and it doesn't work in the practical sciences. And in order to get them to think like a scientist, you have to get them to stop thinking numbers and start thinking measurement. And it's a very hard thing to change something someone has grown up with basically from infancy. And these ideas are not hard to understand, but reversing a decade's worth of continually reinforced habit is very difficult. Ask someone who's been smoking for 10 years how hard it is to quit. Ask someone who has been raised and steeped in a particular culture. And then they find out, oh, there's aspects of that culture I don't like, and I want to change. I want to be different now. How hard is that? It's tremendously difficult. we're talking about nothing less than changing everything that you think about in terms of number. If you were to decide that at 15 or 16, you were going to pull up roots in America and you were going to move to a different country in a different part of the world where it was a different language, where English was not commonly spoken, how long does it take you to be really fluent in not only the language of that new country, but its culture? I would say that this is going to take you a number of years. Certainly, that's the experience of the ESL teaching community with students who immigrate to this country from other parts of the world and come in and start learning about American culture and the English language. It takes a while not only to be lingually fluent in a language, but culturally fluent. So you're not making faux pas because you're thinking about the other culture. How many times have we heard about things like, oh, us in America, we hear homeschool math is tricky to teach. I don't necessarily think so. This seems like an explanation on why every woodwork project turns out needing some form of motivation to get it into place. Thank you, Osmosis 007. Yes, I think so. And woodworkers understand, oh, the whole measure twice, cut once thing. We say, oh, yes, we have this understanding that there's the plans and then there's the wood. And between the two, the only thing that lies between me and a finished project, which actually looks like a table or a chessboard or whatever, is my skill in practically working with measurements and the materials. I'm trying to get my 7-year-old and my partner to look at estimation before calculating. Any advice? I can tell you what works for me, and that was calculators face down on the desk. Okay, fine. You're welcome to use a calculator as a tool, but not as your brain. And in my class, I said, who knows what this is? And everybody said, it's a calculator. No, it's not. It's an electric liar. Because a drunken monkey with a broken thumb can push buttons and eventually hit the equal sign and get an answer. But the quality of the answer that comes out depends on thinking machine number one. So I would tell my students, calculators face down, look at the problem, think through it, get an estimation. Oh, rock is falling 5 meters, gravity, let's see, that's about 10. And so V final, square root of 2 times A times 2 times G times height. So 2 times 10 is 20 times 5 is 100. The square root of that is 10. My estimate of how fast is the rock moving after falling 5 meters, 10 meters per second. And I write this down. And then I go ahead and I do the calculation. Okay, got your answer? Is it written down in ink? Because pencil is erasable. And I say, what's this answer? Square root of 2ax. So 2 times 9.81 meters per second squared times 5 meters height. I square that up, and then I take the square root of my answer, and I get my calculator says 9.9045444112. Lie. That's way too precise. If I'm doing 5.0 meters and 9.81 meters per second, the least significant figures is going to be 2. And so my answer here is going to be 9.9 meters per second as the final velocity. And I estimated 10. I would say my confidence of that answer on a 1 to 10 scale would be a 10. Because calculator and estimate from computer number 1 and calculation from computer number 2 both make sense. And so I can say, yes, I'm willing to accept and then properly round what the calculator gives me. And Josh, that's the way I taught students to think about any kind of mathematical problem. And the idea that, oh, we get these nice, neat answers. That's the other problem with math curriculum. They tend to give problems where the answers come out nice and even? The answer is 2 pi. The answer is, 14. The answer is 22. The answer is 4x. And you get these answers that come out nice and neat. But you know what? When you're dealing with measurements made with tools which have real limitations to their accuracy, and whether I'm talking about this kind of tool for measuring, or I'm talking about this sort where I have, here, this measures down to a 16th of an inch, or if I've got a laser rangefinder that measures down to a millimeter, so we're talking a thousandth of a meter, that instrument has a definite limit to its accuracy. And in digital measuring tools, calipers, scales, rangefinders, the answer will come up to a certain level of, you take a digital scale, you're cooking in the kitchen, you have a digital scale for ingredients. It probably measures to a 1/10 of a gram. And you might say, well, why doesn't it measure to a 10,000th of a gram? Well, certainly you could buy a scale that's that accurate. It's, number one, very expensive, and two, plus or minus a couple tenths of a gram for your cake or your pastry or your pizza crust won't make any difference. So we come up in science with the idea that, gee whiz, our tools need to be accurate, but then there's the question of how accurate do they need to be? What is the accuracy required by my job? And if I say, this is the James Webb Space Telescope, and I'm trying to find the structure of galaxies 12 billion light years away, that thing needs to be pretty darn precise to see something so small, so dim, so far away. On the other hand, if I'm making a cutting board for my kitchen in my shop out in my garage, you know what? Plus or minus a 1/4 inch or a centimeter, it's not going to make a difference for a cutting board. If I'm making a chessboard now, that means all the squares probably have to be precise, perhaps to a fraction of a millimeter, so the whole thing fits together and the square pattern looks right. What level of accuracy does my job require? What kind of tool does it take to measure that? And then once I use a calculator on those measurements, guess what? We can't lie about how accurate our tool is. My paper ruler will not measure protons. Sorry, no way, no how. I used to do a funny thing in my classes. I would do like it was a late night infomercial. The Amazing Wonder Ruler by Barthco. You can measure a proton with my amazing paper ruler. Wait, now how much did you pay? But wait, there's more. And you would go through the whole thing, and they would say, well, that's silly. And I would say, of course. Because when we lie about the quality of our tools, and calculators routinely lie, because we don't take the calculator and punch into it what the quality of our tool is. That's up to us to interpret as scientists. I still remember playing with Don's slide ruler. I wish it was still taught. Changes how you think about a problem understanding. Yes, it does. And in fact, of course, I have one of those in my office library. And here we go. Here we go. This is a nice Pickett. This is a model 1010T Pickett slide rule. And here we go. And I'm trying to get something. Maybe if I'm out of the frame, it will focus on this. My camera's having trouble focusing. Let's move it in a little closer. No, my camera is just not going to focus on something this precise. I'd have to get into manual focus. But the way this works, folks, it has logarithmic scales, and you slide and you do calculations, and then you read your answer. This is lovely because it's a tactile machine. It automatically limits your precision and the number of significant figures you can get out of it, unlike the electronic gadget, which will lie to you and say, oh no, 12 digits of accuracy on your problem are possible. What about addition versus multiplication versus exponentials? We're getting really into the weeds here, but essentially, addition is a different thing. There's no multiplication involved, so the error is not multiplied. Let's say you had a measurement of 10,000. I don't care if you're talking kilos or meters. And you say, okay, let's add on to that. At some point, if the numbers you're adding don't have significant, if they're not accurate to a significant scale, they are effectively zero. If I'm measuring 10,000 meters, let's say I'm measuring, it's 10 kilometers, so I'm going ahead and I'm measuring a race course for a 10K run. It's 10,000 meters. And I measure this off. If I make an error, or if I say, oh, I'm going to change your race today, guys. I'm going to add 1 meter. You're going to have to run 10,001 meters. The job of the runner is effectively not changed. It doesn't make any real difference, because the question is, when you're adding, are you accurate? Are you measuring 10,000 meters accurate to a single tenth of a meter? Then yes. You're actually measuring 10,000.0 meters, then yes, adding or subtracting 1 makes a difference. If we're using exponents, then essentially with the exponents, again, when you multiply two numbers, I'm assuming you're talking about scientific notation. When you multiply two numbers in scientific notation, and again, you find out, does this in fact, if you multiply 3.5 E14 by 2.1 E2, you'll find out that changes almost nothing. Do we have to include error ranges, or is there a rounding rule? Scientists, when they measure results, do include error. That's what error bars are. If you've ever seen a graph with a point and the bar that extends, that is in fact an error bar saying this is the level of precision to which we know this answer. Good science, if you're measuring data, does require error bar. Just rounding doesn't get it, because an error bar says, in effect, here's my answer, and here's how close I know I am to the answer. You see data with big error bars, you don't trust that very much. You see answers with small error bars. The assumption is that the honorable scientist or team of scientists working on this have refined their measurements and gotten them. But again, we're getting very, very far into the weeds here. The whole message here for today, two things. One, number and measurement are indeed different. And two, when we teach about science or think about science or do science, we must have a respect for the accuracy of our tools, and we must be clear about it. So we're running out of time today, and I appreciate all the comments today, folks. I really do. I hope you've enjoyed today's show. You're welcome to email me. And please pick up a copy of Star Mentor. If you have a small telescope or pair of binoculars and you want to learn more about using them and how to master the night sky, reading a star map, and what do I do next with my shiny new telescope, we're starting to get more reviews on Amazon. If you've got a copy of the book, please go ahead and give it a rating, and please take 5 minutes and type in a review. Tell me about your experiences. And of course, if you'd like to contact me about the book, about the show, give me a suggestion for a show you'd like to see, feel free to email me at astronomyforeducators@gmail.com. And we're over time, so I'll just say this is Dr. Daniel Barth, thanking you for tuning in again to another How Do You Know show, and we'll see you next week. Thanks, everybody. Bye-bye now.